Hey guys, hope you're all doing well. So we're on lesson 5 today. We will be learning how to write a function rule given a table of values. So this objective is pretty important. This tells you exactly how we'll do it. We're going to first find the rate of change, and that rate of change, remember, can be called the slope, so therefore we're going to use it as the coefficient of x, because we are only going to be writing function rules for linear functions. We won't worry about writing a function rule for other types of functions. Maybe we'll look at a couple today, but it's not mandatory for your quiz or your test. You definitely have to know how to write a function rule for a linear function. Remember, linear functions are written in the form of y equals mx plus b. So we'll wind up writing it in our notes. We're going to go over the do now. Be sure to go and check your homework answers that were provided for you. And of course, we'll do the development together. And at the end of this lesson, you should know if a function is linear or nonlinear just by seeing a table. And you should be able to tell me the form that we like to write our linear equations in. Your homework is the problem set, and it's on pages 27 and 28. So remember that a function has a rule, and each input only has one output. So this wording is kind of reversed from what we've been saying. We keep on saying that each input has one and only one output. This wording says the same exact thing. There's a unique output for each input. That says that each input only has one output. So let's fill in those blanks. Remember, domain and range are the fancy words for input and output. So above domain, I'm going to write input. And by range, I'm going to put output. Remember, the domain or your input is the set of x coordinates, while the range or your output is a set of y coordinates. So rules can be verbal. They could be an equation. You can get it from a table or from a graph. All of these say the same exact thing. Add 1 to each number. So this is showing that I'm adding 1 to my input. You can see on the x, if we add 1, we get the y value each time we add 1. Since that's what the rule is, we're getting the y value. And then those points were plotted here on the graph, and the rate of change shows like you're going up 1 over 1. The y-intercept shows me that I started at 1. This 1 here in the equation tells me where to start. So we're going to determine the rule. It says to express the function verbally and algebraically. So I'm an algebraic kind of person. I like to look at the rate of change as the change in y over the change in x, right? We learned that earlier in the year. So over here, I'm going to be listing my changes in y, since this is the y column. From 3 to 6, it went up by 3. From 6 to 9, it went up by 3. And from 9 to 12, it went up by 3. Over here, I like to list my changes of x. From 1 to 2, it went up by 1. 2 to 3, up by 1. 3 to 4, up by 1. So I would say that the rate of change for this table, remember, it's the change in y over the change in x, so it's going to be 3 over 1 the whole way through. Since it's 3 over 1 the whole way through, we know it's linear. So the equation would be y equals 3x, because the rate of change is like your slope. And if we write it in the form of y equals mx plus b, I just need to figure out what this b is to give me these answers. Sometimes b is 0, sometimes b is some other number. Remember, b is the y-intercept. A y-intercept has an x coordinates of 0 and a y coordinate of something else. So you can use your table and go back in the chart to try and figure out what would be the y value if x was 0. So 0 comes right before 1, and this keeps on increasing by 1 in the x column. Therefore, I have to follow the pattern in the y column. If it kept on going up by 3, I guess this really did start at 0. So in this case, it's 3x plus 0, or we can just write it as y equals 3x. You can also test this out by substituting in some x numbers to make sure you get the y number. Like if I look at my first x value of 1, if I put a 1 in here, 3 times 1 is 3, and in the y column it says 3. Let's test the next one out. If I plug in a 2, 3 times 2 is 6. In the y column it says 6. So once you write your equation, I suggest that you test it with the table of values. On this next one, we'll do this together as well. This is going up by 2, up by 2, up by 2. And the x values are also going up by 2. So if the slope is change in y over change in x, it's going to be 2 over 2 each time. 2 over 2 simplifies to be 1. The rate of change is constantly 1. It has a constant rate of change, therefore it's a linear equation. So we can write it as y equals 1x plus, let's back this up to 0, back this up by 2. So this time it does have a number other than 0. Let's test it out. So y equals 1 times, I'm going to plug in my first x value and see if I get the y value out of it. 1 times 1 is 1. 1 plus 6 is 7. I made a mistake. So this is why it's so great to test your equation. I definitely made a mistake. I see it. My x's were going up by 2's each time. So if I back this up by 2, I get a negative 1, not a 0. So at negative 1, my y value is 6. So in between a negative 1 and a positive 1 is the 0. In between a 6 and an 8 is a 7. This must be 7. Isn't that great when teachers make mistakes? Because then we can show you where our mistake is. I could just start this video all over and you wouldn't even know I made the mistake, but I'm going to leave it. So I'm going to test this now. Y equals 1 times 1. I'm testing this x value of 1 again. Plus 7. 1 times 1 is 1. 1 plus 7 is 8. Yes, it worked. I am never satisfied with just testing one. I'm going to test another, just in case I made a mistake and I didn't catch it. Y equals 1 times, I'm going to plug in the 3 now. Add on 7. I'm hoping it's a 10. 1 times 3 is 3. 3 plus 7 is 10. Yes, I'm confident now that I'm right. So the answer is y equals 1x plus 7. Of course, you can write this as just y equals x plus 7. So the trickiest part about writing a linear equation is probably finding that y-intercept. So be really careful. Otherwise you make mistakes like Mrs. Dams. But at least I found it. Sometimes our tables are horizontal. Remember, the input are your x values and the output are your y values. So if I'm going to do the slope as the change in y over the change in x, just be really careful. From here to here, it's going up by 14. And from here to here, it's going up by 7. Therefore, the first rate of change is 14 over 7, which is 2. Let's check out the next one. This is going up 4, and this is going up 2. So the next rate of change is 4 over 2. And some people right away think, uh-oh, it's not linear. But let's simplify this. 4 over 2 also simplifies to be 2. So far, both these rates of change are the same. So far, it looks like it's probably linear. Just want to make sure the whole way through that the rate of change stays 2. So from 11 to 33, it went up by 22. From 5 to 16, it went up 11. 22 over 11 is 2. So far, so good. From 33 to 51, it goes up 18. From 16 to 25, goes up 9. 18 over 9 is 2. And finally, 51 to 63. This goes up 12. This goes up 6. 12 over 6 is 2. It's linear. The rate of change is 2. So y equals 2x plus, and now this is what I have to fill in. There's another way of maybe figuring out what your y-intercept is without trying to find the 0, because that might be a little tricky. Sometimes I use kind of like common sense. I'm going to pick an x value that's not too hard to deal with, so I'm going to pick an x value of 3. And put in a 2 times 3 here. Now I'm going to mentally figure out what do I have to add to it so that I do get out this 7. So 2 times 3 is 6. Don't you agree all I have to do is add on 1 and I get my 7? So this should be the right answer, but I'm going to test it with another value of x. I'm coming over here because I'm running out of room. So I think the equation is y equals 2x plus 1. I'll test it with an x value of 5 and make sure it works. 2 times 5 plus 1, 10 plus 1 is 11. It did work. So I'm satisfied that this is my answer. So did you see that once you find your rate of change and you put it as the coefficient of x, you can then plug in one of your x numbers and use your common sense or your logical thinking to figure out what must I add on so that I get the value I want. So let's do the next one. I guess the same way. So this is going down by 15. Well, this is going down by 3. So negative 15 over negative 3 is a positive 5. This goes down by 1 and up by 1. Negative 1 over 1 is negative 1. This goes up by 4 and up by 2. 4 over 2 is 2. Up by 5, up by 1. 5 over 1 is 5. Up by 16 and up by 2. 16 over 2 is 8. Do you notice that the rate of change is not constant? This is not linear. So for your homework, you don't have to write the equations of things that are nonlinear. If you really just kind of use as much common sense as you possibly can, maybe you could figure out this equation. Since it's not linear, remember that the exponent of the x isn't a 1. So I'm going to think about maybe the exponent being a 2. And honestly, what I can see using my logic or my common sense is that the equation is probably x squared minus 1. Let me show you how come. If I plug in this first x value of -1, I have -4 squared minus 1. -4 times -4 is a positive 16. 16 minus 1 is 15. So it gave me my first one. If I test it with the next one, -1 squared, -1 times -1 is positive 1. 1 minus 1 is 0. It worked with the second one. So I'm right, but please no worries about this. It's not mandatory for you to know how to write an equation for a nonlinear function. That would be like maybe a bonus if we were to give you some kind of question like that on a test. So Tim's salary as a lifeguard depends on the number of hours he works. If he's paid $9 an hour, what is his salary for 3 hours? So 9 times 3 is $27. What about for 12 hours? 9 times 12, $108. I just pulled up my calculator for the next one. So 22 hours, 22 times 9 is $198. So is his salary a function of the hours he works? They're asking, is it a function? The reason why is it a function of the hours he works is because the hours are your input. His salary changes depending on how many hours he works. But of course it's a function, right? For a certain amount of hours he works, he is going to get out one salary. He's not going to have like a choice of salaries. So yes, because each input only has one output. For each set of numbers of hours he works, he gets one salary out. If possible, write the rule, then create a table of values. So it is possible. The words really are up above, but really it's $9 times the number of hours worked, and that's what equals his salary. So I'm going to use Y for salary. X will be the number of hours. So Y equals 9 times the number of hours. That's it. And we can fill in this chart even with the numbers up above. When I put in a 3, I get out a 27. When I put in a 12, I got out a 108. And when I put in a 22, I got out a 198, because we did Y equals 9x. So here we did 9 times 3, 9 times 12, and 9 times 22. So this is a pretty similar equation. Instead of hours and money, now it's minutes and distance. So the distance that Missy rides her bike depends on the number of minutes that she spends riding her bike. So I guess the more minutes that she rides, of course, the farther she will go. So it definitely is a function. Is the distance she rides her bike a function of the number of minutes? And the answer is yes. For each input, which is number of minutes, there is one output, which turns out to be her distance. So we can answer these questions up here about what distance does Missy ride her bike in 15 minutes. And it says that she rides her bike at a constant rate, which means it's linear, of 0.15 miles per minute. So 0.15 miles per minute means that I multiply 0.15 times 15 gives me 2.25 miles. 0.15 times 30 4.5 miles, and 1 hour. Notice it says hour, but this is miles per minute. So I have to change this hour to 60 minutes. You can't just plug in a 1 because that would mean 1 minute. So be careful of your units. I have to do 0.15 times 60. I get 9 miles. Makes sense that the longer she's riding for, the more miles she can go. So in words, her distance is equal to the rate times the time. Do you remember we kind of talked about this in our scientific notation unit? Distance equals rate times time. So her distance equals 0.15 miles per minute times the minutes, the number of minutes. So I'll use y for distance, 0.15, and I will use x for minutes. I just let y equal the distance in miles, and I let x equal my number of minutes. So we can put these 15 minutes, 30 minutes. This I'm going to write as a 60 instead of 1 hour because our input is in minutes. And my output, 2.25 miles. 4.5 miles and 9 miles. So this next question is asking us if the cost is a function of the number of items, meaning that for every number of items we put in, do we get a different cost out? And the answer is no, and it's right here. 4 items cost $6, but over here 4 items can cost $15, so no, it's not a function, because the input of 4 gives 2 outputs. So it says if possible, write the rule. It's not possible because it's not a function, so we're not going to write a rule for this. Number 4, is the price a function of the number of donuts? Should be. 1 donut costs that, 2, 3, yes, it's a function. Each input, which is the number of donuts, gives us a different output, which is the cost. So write a rule if possible. Skipping the words. Rate of change would really be how much it costs per donut. It looks like if 1 donut is $1.25, I guess it costs $1.25 per donut. So if that's true, it means if I multiply the 2 by $1.25, I should get that cost. Is it $1.25 for each donut? If I multiply by 2, I get $2.50. Is it $1.25? I'm just checking with the 3 donuts to make sure. It is. Each donut is $1.25. I am going to write some words. Which means that this is the rate of change. So $1.25 times the number of donuts. And the y-intercept would be 0, because if you bought no donuts, you're not spending any money. So some plants need a large amount of space in order to grow. The number of seeds that can be planted in each row is related to the length of the row. Examine the table below. Does the relationship represent a function? So these inputs, each one has its own output, so it is a function. And then, if possible, write the rule. So it looks like I could do 16 divided by 4 to give me a 4. 24 divided by 4 gives me 6. 52 divided by 4 gives me 13. And 64 divided by 4 gives me 16. So I just kind of used my common sense here. I didn't even do the rate of change. I'll show it to you using the rate of change also. But sometimes you could just use your common sense, right? So it looks like the equation would be y equals whatever the x value is divided by 4. Do you know another way of writing this is y equals 1/4 x? So take a look if we go and do the change in y over the change in x. This is going up by 2, while this is going up by 12. I mean 8. And if I write this rate of change, 2 over 8, it equals 1/4. Notice it matches the equation I wrote. So if you can write the equation just using your common sense, that's also acceptable. Is this a function? Does each input have one output? The answer is yes. Can you use your common sense on this one? This one's not linear, but I could see that if I square the x, I get the y value. 2 squared, 2 times 2 is 4. 5 squared, 5 times 5 is 25. 6 squared is 36. 4 squared is 16. Remember, you're not going to have to be able to write the rule for a nonlinear function. We could prove it's nonlinear by looking at the rate of change. From 4 to 25, it went up by 21. And from 2 to 5, it went up by 3. So the first rate of change is, I'm going to write it over here, 21 over 3, which is 7. The next rate of change now goes down by 25, and this goes down by 5. So negative 25 over negative 5, this is now a positive 5. So this is a rate of change. This is a rate of change. It's not constant. So this is a nonlinear function. And it's nonlinear by the equation because the exponent's a 2. It's nonlinear by looking at the table rate of change. part B is not a function because the input of 1 has 2 different outputs. And the rest, you're on your own. I just want to point out that you have to state whether each table is linear or not and tell me why or why not. So since we're looking at a table, you're going to be looking at the rates of change. If the rate of change is constant, then it's linear. Remember, rate of change is change in y over change in x. If constant, then it's linear. If it's not constant, then it's non-linear. And you're going to write the rule for the tables that are linear functions. Okay, if anything turns out to be nonlinear, you don't have to write that rule. Don't get fooled if it like skips some numbers. Remember, sometimes a ratio, a change in y over change in x, sometimes it simplifies to be constant. So be really careful with that. And send any questions our way. Talk to you soon.